So thank you very much, Gerd, for the kind introduction and also for the invitation to talk here at one of the oldest international... You cannot hear me? Test, test, test. Can you hear me? No sound yet? Test, test, test. Gerd, can you hear me? You can hear me? Henry, I see Henry can hear me, but Gerd, you can't?
Okay, then maybe it's just me. So.
What about the others? Andre, you can hear me, so I see some people putting the thumbs up, but unfortunately, Gerd, you can't hear me. Okay. Anyway, Gerd, so thank you. Maybe you can read from my lips. Thank you for the kind introduction, Gerd, to give the keynote here. I'm a little bit sad, of course, that I can't see you guys all face to face, and hopefully next year the situation is better and we can have face-to-face meetings again. So today, I would like to talk in my keynote about blended realities and how human imperfection can be used to improve the experience in such blended spaces. And blended realities are nothing special. Actually, we live in a digital world in which reality and virtuality, as well as natural and artificial intelligence, are increasingly merging together. So our own reality has evolved into a blended space, which is composed of the dichotomy of natural and artificial objects. And according to the German philosopher Bimbacher, the distinction between natural and artificial occurs at the impact level. So natural denotes everything that became without human being, and artificial, everything which has been made by human impact. And although this distinction is central to our own orientation in the world, artificial flowers or trees artificially planted by humans or genetically modified food show the blurring between the natural and the artificial. And also our own field, computer science, is evolving to a blended space. In classical computing, as you all know, data is encoded in fundamental units called bits, where each bit represents a distinctive state, which is either 1 or 0. However, we also observe here a shift from this classical model of computing towards other approaches, such as quantum computing. And here, data is encoded in so-called quantum bits, which can either represent a 1, a 0, or a coherent superposition of both states simultaneously. And with this probabilistic approach of qubits, the area between 1 and 0 can be considered as a continuum, as a blended space. And this technology promises further performance growth, which will ensure further exponential growth of technology in the future. In my talk, I would like to talk about 3 different fields in the area of artificial intelligence, mixed reality, and robotics, and show how they all blend together. So let's start with mixed reality then. Mixed reality, as you know, is the combination of real and artificial environments presented via some sort of immersive or semi-immersive technology. And we know that also mixed reality is a blended space that brings together real and virtual objects. Paul Milgrom introduced his famous reality-virtuality continuum. And if we consider real-world objects on the left side, such as these 2 broken vases, and virtual objects on the right side, such as a virtual vase with flowers, there are essentially 3 different ways how we can blend between reality and virtuality. First, we can augment real-world objects, for instance, by adding virtual flowers in this real vase, similar to Milgrom's mixed reality continuum, resulting in augmented reality or augmented virtuality, depending if you come from the left or from the right side. Next, we can also diminish objects, for example, by removing the broken parts of this vase here, resulting in diminished reality and diminished virtuality, depending again if you come from the left or right side. And finally, we can also modulate real-world objects by changing the appearance without actually adding or removing any objects, sometimes denoted as modulated reality or modulated virtuality. And I think this is a finer description of how to get and blend and merge reality and virtuality or vice versa by augmenting, modulating, or diminishing objects. So my former PhD students and now postdoc Susanne Schmidt built such a blended reality space during her PhD thesis, consisting of a cave environment, which also was equipped with movable projectors and depth sensors, which allow to superimpose also 3-dimensional physical objects, inspired by some of the work, and I see Henry Fuchs is here, by the work in UNC Chapel Hill. So let's see how such a blended space can be composed. So here's a small video. And by the way, Gerd, is the video playing fine, or is it, so I may, click the checkbox. That's good. So what you see here is a typical cave environment in which you have this physical skeleton of a dinosaur. And this is the typical augmented reality setup in which you just add additional virtual information to some physical real-world object, such as this museum artifact. And in a second, you will see how Susanne is using the depth sensors and the movable projectors to project a virtual skin to this dinosaur. So this would correspond in this case to a modulated reality in which we don't really add virtual objects per se, but change the visual appearance of existing virtual objects, such as, for example, Greg Welch and Henry Fuchs shader lamps. And in the next sequence, we use the feature of trying to let the skeleton of this dinosaur diminish by projecting the background information on top of the skeleton from the corresponding viewpoint of the user, which lead to the diminishment of this skeleton and focus on the background in this case, showing, for example, the dinosaur in its natural surrounding. So, to go a little bit back in time and have a look at who started more or less with this mixed reality, then there's certainly this gentleman here on the right side, one of the pioneers in this field, which we have to mention here, which is Ivan Sutherland. And I had the honor to meet him 2 years ago at the SIGGRAPH conference after the panel that actually Henry Fuchs organized. So I think most of you are aware of the famous essay written by Ivan Sutherland in 1965 called The Ultimate Display. And in his essay, he speculated what an ideal, optimal, immersive experience would look like. And he concluded that the ultimate display would, of course, be a room within which the computer can control the existence of matter. So what does that mean? He gave some examples. So he said a chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining. And a bullet displayed in such a room would be fatal. But he also wrote that with appropriate programming, such a display could literally be the wonderland into which Alice walked. So the ultimate display would be a computer-mediated reality which gets indistinguishable from the real world. And this notion of a virtual reality environment is often used in science fiction, literature, or cinematography to question whether we truly know if our perceptions are real or not. And movies like The Matrix, directed by the Wachowski siblings, is a prominent example of this perceptual ambiguity. And actually, the notion that our real world is only a computer-generated simulation has been shown the first time in the German science fiction movie World on Wire, directed by Rainer Fassbender in 1973. And I'm just curious, guys, please use your chat and indicate if you have seen this movie. So feel free just to write it in the chat. I guess not too many have actually seen this movie. I have a copy in my room. It's a very boring and lengthy movie, but there are really some interesting indications towards the simulation theory. Already 5 years earlier, before this movie came out, Ivan Sutherland was able to build one of the first prototype of such an ultimate display. And here you can see original video footage. You see the Sword of Damocles, which was referred to the linkage tracking technology, which made sure that the system knows where the user is looking at. And it's very similar to today's optical see-through technologies, using some beam splitter technology, allowing to see the real world and superimpose it with virtual graphics, as you can see this wireframe cube in the past. And obviously, immersive technology has made enormous progress in the last decades. And here's one recent example from Microsoft showing an augmented reality setup. And they show an application called Spatial I/O, which, for example, allows you to collaborate with virtual human characters, which are controlled by actual humans, so avatars, which you can actually generate by using artificial intelligence based on a two-dimensional picture only. And which also support, of course, human body language, since it tracks the head as well as the fingers using the Microsoft HoloLens 2 tracking technologies. In the same way, we also see that virtual reality displays have made enormous progress. Here's a marketing video from Oculus Quest 2, which is probably the best head-mounted display available nowadays, if you also take into account comfort and price. And here, guys, I'm also interested. So how many of you have tested the Oculus Quest already? So I haven't had the chance yet. Please use the chat if you have tried the Quest 2. not yet, not yet, not too many. Okay, so, and though these technologies, I think, really have made significant improvements, we are still not yet there. So these displays and also the environments that we can produce in AR and VR are still not perfect, but we're actually getting there. But there are also more dynamic scenarios with seamless transitions and interactions between reality and virtuality. And this is something we would like to refer to blended spaces. And I would like to take you a little bit to a journey, what an ultimate blended space would be. So let's reconsider some of the visions from Ivan Sutherland. So he wrote that a chair displayed in such a room would be good enough to sit in. So that means that in one moment, a chair could be diminished and I can't sit on it, but in the next moment, a chair is added to the scene or modulated and I can sit on the chair. There's no need to switch glasses or change the display environment, but the entire experience appears to be seamless. And we refer this as reality, virtuality, seamlessness. The next vision was handcuffs displayed in such a room would be confining. So virtual objects can affect real world objects and vice versa. And we will refer the ability of real and virtual objects to interact with each other as reality, virtuality, interactivity. And finally, he wrote that the bullet displayed in such a room would be fatal. So virtual objects can transform from virtual to real objects and vice versa. And we will refer this to reality, virtuality, transformability. And this brings us to the definition of a blended reality space as a reality-virtuality continuum or environment with one or more real as well as virtual objects and actors which support transformability, interactivity, and seamlessness between real and virtual objects. And still today, we neither have perfect mixed reality, nor do we have perfect blended spaces. And I would argue that it doesn't have to be perfect. According to the philosopher Horowitz, perfection itself is imperfection. And more precisely, Lucilio Vanini formulated it, the greatest perfection is imperfection. And though we can't build perfect ultimate blended spaces or mixed reality experiences today, at least we can exploit human imperfection and use some illusions to make people believe that we actually have a perfect blended space. So let's have a look how the human information processing actually works. So whenever we move through the real world or virtual world, there is multisensory information which comes and pours into our senses. Of course, this is visual sense, this is the auditory sense, the tactile sense, but also the inner body senses like the vestibular, proprioceptive senses, and so on. And this information is then processed in a bottom-up way, for example, by processing optic flow information. And on the same way, the cognition interprets these movements or our actions that resulted in the corresponding multisensory stimuli. But at the same time, also the cognition affects perception based on prior experiences or influences the perception in a top-down, more hypothesis-driven way. Then cognition guides our motor actions, but again, at the same time, bottom-up revision regulates our actions. And finally, we have motor comments, which are initiated and affect the environment. So for example, we change our head position, we move through the space, or we interact with our hands, which then again results in observed sensory feedback, either with our internal or external senses. Mixed reality now is typically changing the mapping between our motor comments and the environments. For example, by changing the view when we move our head, which is tracked by a head-mounted display, or some other tracking technologies, if we grab, for example, with a glove or a tracked hand in the space, or if we simply move in a computer-generated environment. Now, at the same time, when those motor signals are sent to our muscles, which can then be tracked, our internal system is using a so-called afference copy signal. This copy signal is used in a forward model to predict the sensory feedback. And typically, we then have a comparator which compares the predicted sensory feedback from the forward model with the actual observed sensory feedback. And typically, there is always a sensory discrepancy between what was predicted and what we observe. In the real world, typically the difference is so small that we are not aware of any discrepancies and we will just adapt our motions to the new feedback. However, even in the real world, we have situations in which we can actually observe a sensory discrepancy. So if you think, for example, you want to lift a box and you totally underestimate, for example, the weight of the box. So in this case, you will clearly observe that there is the sensory discrepancy between what you predicted and what you actually observe. In particular, in mixed reality environments, there is more sensory discrepancy, which is induced by the technology itself. So based on or due to latency, tracking errors, inaccuracies, or imprecision of any sensors and actuators. However, again, if the discrepancy is small enough, people will not notice and simply adapt their motor control, as long as the multisensory integration of the different sensors result in a plausible observed feedback, which is not too different from the predicted sensory feedback. So let's have a look how this multisensory integration actually works. There are essentially two models which describe how stimuli from different senses can be combined. We focus here on the first one, which is the maximum likelihood estimation. Here, the idea is that each stimuli from a different sense is weighted in the Q integration process. And the weight specifies typically the reliability of each sense. So for example, very often vision gets a very high weight, which means a high reliability, and therefore can dominate, for example, other senses in this integration process, such as vestibular or proprioceptive information. So one of the reasons why vision gets usually such a high weight is that most of the information that we receive is based on the visual channel. And this visualization shows how information from the different senses pours into our, from the different stimuli pours into our senses every second. And here you see that the sense of sight is the fastest. It has the same bandwidth as a gigabit Ethernet. Then you have touch, which is about the speed of a USB key, and you have hearing, smell, which have comparable throughput to a hard disk, and taste. I haven't focused here on vestibular, proprioceptive, or other kinesthetic senses. I would like to draw your attention to the very small white square on the very bottom right of this graph. And this shows the amount of information which actually pours into our conscious short-term memory. So this is the only information which is actually further processed in our human information circle. So that means that a lot of the information which comes to our senses is actually not further processed and used in our perception action loop, which I just showed you. And I just want to give you two examples. So Gert, this is a picture for you, since you also have been in Hamburg before. So that's the beautiful city of Hamburg. And if you want to display such a high resolution image for the entire field of view, you can take into account the visual acuity, which is approximately 0.3 arc minute. And if you find now a large screen, which supports approximately the 180-degree peripheral information on a head-mounted display, there has been some math which calculated based on the 0.3 arc minute that you would need about 576 megapixels resolution. And if you calculate now, you would represent every pixel with maybe 3 bytes. That would mean you would need 1.5 gigabyte per frame, which you need to transmit. And if you think about the fastest HDMI cables that we have so far, supporting approximately 10 gigabit, that means we will be reduced to 10 frames per second if we want to have displays supporting the resolution of our eye. However, here's the good thing. If we focus on our eye on certain objects in the environments, actually we perceive a sharp image only on a very small spot, which is called the foveal area. So the foveal region in our eye approximately considers 2 degrees field of view. And that means to render a sharp image only in this very small portion of our eye, we would just need 7 megapixels. And vision is really blurred in the periphery. Of course, we never observe that because typically wherever we look, there is a sharp image. But if you focus, for example, and you try to read a text, you will clearly see when you have your eye still that you a couple of centimeters left and right from the spot where you focus, you're not able to read anything, which shows the blurring of the peripheral image. So for the entire peripheral, it has been calculated you would need 1 megapixel. So that means in total, you would just need 8 megapixels to support the full visual acuity of the eye. And of course, you need to know exactly where the user is looking at. And currently, HMD manufacturers work, for example, on movable screens to make sure that you track exactly where the user is looking at and use a small, high-resolution screen to give you these 7 megapixels, which are there. The other thing, many people work on foveated rendering techniques, also allowing high-resolution rendering, where we actually look to also decrease the required bandwidth for the rendering process. So that's an example in which information is filtered out by our senses, and we can make use of this human imperfection. The next thing I would like to show you is an example which illustrates how information is processed. And some of you have seen this video before. If not, that's a small sequence in which you guys have to solve a murder crime. And I want you to carefully watch the following scene and pay attention.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
That's right, madam.
It's just a matter of observation. The real question is, how observant were you?
Okay, so he asked, how observant have you? So some of you might have noticed some strange things or odds during the sequence. So let's have a look at the start sequence of this movie, which looked like this, and have a look at the end scene of this movie. And some of you might have seen that during the movie there were some changes actually happening. So some of you might have observed that the color of the detective's coat has changed, or that the vase and the flowers in the on the table have changed. But I guess that none of you have seen more than the other 20 changes which occurred during this very short video snippet. And I would like to show you the video once more, but from a different viewpoint, to see how those different changes actually occurred.
And action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So that's essentially an illustration of how many information that pours in our senses is not further processed by our short-term memory or long-term memory. And again, we can make use of these imperfections of the human system to improve our visual experiences. So I would like to draw the attention to those aspects that we just observed, which go unnoticed when we perceive information. The first thing is perceptual filtering, which I just mentioned with the visual sense, which blurs the peripherals, but it also works with other senses, such as in audio, in which we have masking, for example, of sounds. The next example we just saw is selective attention, as seen as these change blindness or inattentional blindness in the detective video. And again, this can also be observed in other senses, such as audio and tactile information. Many of you might have heard about the cocktail party effect, for example, in which I can listen to somebody, even if there is a large crowd, by decreasing the perceived background noise of other people talking, by focusing my attention on a specific person. And motor adaptation, we talked in the beginning, also allows us to quickly react to small sensory discrepancies. And what I would like to do now is I would like to focus a little bit on each of these aspects and give some examples how we can use this. So let's start with motor adaptation. And here I would like to focus a little bit on redirected walking. So coming again to the last sentence of Ivan Sutherland's essay, he wrote that the wonderland into which Alice walked. So he refers to a virtual reality system in which we can explore the environments in the most natural way. And this is not by using a mouse, a keyboard, or any other strange gestures in space, but just by using real walking, our gaze. Obviously, implementing real walking in VR or AR is rather easy. You just simply need to map your motions one-to-one to virtual camera motions. However, one of the problems arising is that typically the real environment in which you can get tracked is smaller than the space that you want to explore. And the problem is that typically when wearing a head-mounted display, you're not aware of your real-world boundaries. And here is a video which actually shows what could happen if you're not aware of these environments. So that's a video Evan Zuma sent to me. You see a game player who uses an immersive game playing some zombie game, and you will see that she really experienced a high place illusion and plausibility illusion. So really, she believes that a zombie is trying to catch her, and look what happens.
You almost don't get the knife. Oh,
So those things really happen if you have a high sense of presence and really forget about your real world boundaries. There is some solution to this problem called redirected walking, as introduced by Sharif Razak from the University of North Carolina. And here's an illustration of the main idea. So assume that a user dons on a head-mounted display, for example, in a living room or in a lab environment, and assume that the user sees now a virtual environment, like a virtual chair. So if we can predict that the user wants to walk towards this virtual chair, while the user is approaching the chair, we can slightly rotate, for example, the environment around the user in such a way that the user is actually walking on a circular path in the real world, while he or she believes to walk straight in the virtual environment. And one of the interesting things here is that by introducing these changes, you can also change the position of certain objects. This virtual chair, for instance, can now be used to provide passive haptic feedback. So you can actually sit on a chair, one of the visions of Ivan Sutherland. And of course, it's an interesting question how much you can actually trick the users. And myself and many other colleagues have performed a lot of psychophysical experiments to identify how much manipulation actually works. And you see also at the bottom here that with improving technology, improving head-mounted displays, the required radius to trick you has also shrinked within the last 1 or 2 decades. And this also shows that with improving visual quality of the head-mounted display, there is more reliability that in the multi-sensor integration process that we invest on the visual sense. The next aspect I would like to show you is perceptual filtering. So how can we use perceptual filtering to also improve the overall mixed reality experience? So from vision science, we know that when we move our eyes through the environment, there are essentially 3 different states that we use. We have fixations, we have blinks, and we have saccades. The redirected walking I just showed you so far in most experiments have focused on fixations, in which we have this small foveal area in which we see sharp, whereas the remainder of the environment is blurred. However, we also perform a lot of eye blinks and saccades, up to 20 eye blinks per minute and 40 saccades per minute. And during those eye blinks or saccades, the visual input is suppressed. So that means that approximately 10% of the time when we move our eyes in the environment, we are literally blind. Yeah? And this can be used again to induce changes. Here is work of my postdoc, Eike Langbeen, which was presented at SIGGRAPH 2 years ago. And here he performed some psychophysical studies to first track the eye blink. And when the user performs an eye blink, he introduced some changes to the scene, in particular rotations in all directions, as well as translations along all axes in space, and identified how much we can actually induce changes which are not noticeable by the user. And this can then be combined with traditional redirected walking. So here's an example in which a user walks along a spaceship. So we use already some curvature gains here, or being more precise, bending gains. And whenever the user performs a blink, like here, you see that we can induce an additional 3 to 5 degrees manipulation where the user is not aware of such manipulations. Next, I would like to show one example in which we use selective attention to also manipulate the environments in such a way that this information cannot be processed by the human information processing based on the imperfection. So what you see here is Lucy Kruse, who is a PhD student in my group and is testing one of Eike's systems. And this is inspired by passive haptics as introduced by Love Kohli, also from UNC, as well as redirected touching, which has also been used by Microsoft and Love Kohli before. So what you see here is a user taking this virtual or physical sphere, which provides passive haptic feedback for a virtual globe. And as you can see, she leaves the room now, turns right along a corridor, and enters a different room. And in this different room, there's another virtual table, and now she has to place this globe on the same physical table, whereas it was a different table in the virtual world. And here is another video illustrating how this actually works. So you see the purple area here, which denotes the actual tracking space. And you can see while the user is walking around the corner, the virtual rooms are switched. Yeah? So in this case, the user takes, I think, a key card to open the other lab. And in a second, you see that he is leaving the room, turns right around the corner. And after the corner, the virtual room is switched. And here is the switch. So this is called impossible spaces, as introduced by Evan Zuma Rosenberg from the University of Minnesota. And here's another example how you can use rotation gains. So this is a task in which the user has to move these lasers from A to B. So we try to induce some head rotations by performing this interaction. And during those interactions, we can induce rotation gains. That's very similar to something that Tabitha Peck has introduced with her distractors work, for example. And here's a last video of the same application, which we presented last year at SIGGRAPH. And here you see a top-down projection of the environment, which illustrates a little bit better how the actual manipulations are performed. So you see that the entire environment is slightly rotating while the user is walking. And you can also see how the ground projection of the different rooms is changing once the user has left the room and is moving towards the other room. And again, this makes use of inattentional and change blindness, since as long as we do not focus our attention on the actual layout of the rooms and how they are connected to each other, we can actually trick the user here by using this selective attention as some means of imperfection of the human information system to reduce the amount of information that we need to process. And you can apply this to walking, but also to touching. Here is an example of redirected touching. So the idea is here, the user is always touching the same physical object in the center, these green cube. But due to, again, manipulating the mapping between real and virtual hand as tracked with the lead motion controller here, you can, in the virtual world, guide the hand to one of the other cubes here in this example. And again, we make use of perceptual filtering on selective attention and motor adaptation and trick the system and make one object a passive haptic object for multiple other objects. Okay, let's have a brief look at intelligent virtual agents. So artificial intelligence is a hyped topic, as hyped as virtual reality like 2 or 3 years ago. And the idea of AI is that it simulates human intelligence. So it simulates the ability of humans to perceive, learn, decide, and act. And actually, there is not a common definition of intelligence. And Alan Turing was one of the first to think about actually what is an artificial intelligence. And he took a behavioral standpoint and asked the question, can machine do what humans do? And he proposed one very famous example, which is the Turing test, an imitation game. So this is illustrated here. So a user, C, denoted with C here, communicates in a text-based chat only with either a computer, illustrated in A, or a human being in B. And if the computer A is able to trick the user to make him or her believe that this is actually a human user, then the system would have passed the Turing test, which hasn't really been passed until today. There are some reports, but it's not really conclusive. And there is actually a Loebner Prize, which hasn't been given away yet if you pass the Turing test. However, today we are pretty good with agents. So here's one example from my postdoc, Susanne Schmidt, who developed a Unity 3D model, combined it with IBM Watson to process real-world information based on sensors such as cameras, microphones, so that this agent is able to process speech, gestures, and also other information stored in databases. And here's a video of the communication with this agent.
Hello.
Hello, how can I help you?
Tell me about HoloBalance.
In the HoloBalance project, we utilize holograms for personalized virtual coaching of elderly people with balance disorders. I can show you some project videos if you like. Are you interested in one of them?
The second one looks interesting.
Okay, here we go.
That's enough.
Do you want to see another one?
No, thanks.
Okay, maybe next time.
See you later.
So you see this works already pretty good, and it's quite plausible actually. But again, those agents will never pass the Turing test. So it's not an ultimate Turing test experience. And the reason for this is an agent does not have to be super intelligent to pass actually the Turing test. We humans are not intelligent per se, and we also induce some unintelligent, imperfect behavior, as we just have seen. So in order to pass the Turing test, you would also have to mimic some of this unintelligent behavior. And here's an interesting example from Google Duplex, I guess many of you might know. Here's a sequence in which you can use Google Duplex to make a phone call for you as an assistant. And here Google Duplex is making an assist or an appointment for a client.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second.
So the last sequence is quite interesting. So it takes a second or so until people realize what actually happens. So this Google Duplex is not using perfect natural language processing, but it mimics some of the imperfections of the human speech by using some stutter or delay sounds. And we are really getting interested in exploring how we can also induce some of these imperfect human behavior into agents. So here's another example of this agent, Louise. And I'll just play the video and give you some details about it afterwards.
Hi, Louise. Have you seen Frank today?
Yeah, I saw him in the lab
So
around
here are
noon.
just some aspects which we just copied from Google Duplex. So I want to focus you on the visual appearance of the agent. So we have now some blemished skin, some birthmarks. Also during the natural language processing, when she was thinking if she has seen me or not, she was actually moving her eyes upright. So this corresponds to visual memory task. At the same time, she was also some stuttering and delay sound like and also inducing some uncertainty. And finally, her actual answer was rather vague. So she said she saw me around noon. Yeah? And this is, of course, something which is not like a super intelligent behavior. It uses some of the imperfection that we use typically in day-to-day communication. And we think that this might really improve natural communication and might also actually affect in a positive way trust or social presence when interacting with agents. Okay, coming to the last aspect for the blended spaces, which is the Internet of Robotic Things. So here's the idea to bring together autonomous robotic systems, the Internet of Things, and cloud computing by using connected sensors and actuators. And here are just a couple of video snippets I would like to show you, which combine mixed reality and artificial intelligence and robotics. So here's my postdoc, actually former postdoc, Dennis Krupke, who uses a Microsoft HoloLens, gaze and speech to interact with this robotic shadow hand. And in the mixed reality environment, he can see, for example, pre-visualization of what the robot would do if the corresponding command is initiated, with the idea to also provide some security and prevent collisions with the robot. Another example of Julia Hertel, also a PhD student in my group, who's using some VR and mixed reality technology, for example, to control a drone. And another video snippet of Jingxing Shang, also PhD student who works with mobile robotic platforms. And here he uses mixed reality, for example, to display humanoid representation on robotic devices by also using our natural ability to automatically understand, for example, space and distance when we interact with other human beings. And for the remainder of that talk, I would like to briefly summarize how we can bring this all together. Here's one example in which we build a device which combines proprioceptive pseudo and tactile information in a mixed reality environment using some AI for the signal processing, as well as robotic devices for providing the feedback. So here we have EMS, so electrical muscle stimulation, and tendon electrical stimulation, which stimulates the sensory nerves as well as the motor nerves. We use pseudo haptic feedback by using gains between the real hand and virtual hand, and also tapping feedback by using a piezo actuation as shown in this video here. And here's just one example in how far users are using this in an experiment. So you have the combination of proprioceptive feedback provided by the EMS and TES stimulation. You have the idea of stiffness of the device by using pseudo-haptics and the redirection of the hand. And you get the tactile information by the corresponding actuators, which is then all be combined in a multisensory integration process and provides a holistic touch illusion. And the last example I would like to show to bring together virtual agents, Internet of Robotic Things, and in a blended reality space was done together with Gerd Bruder from UCF, who also brought a lot of the inspiration from Greg Welch Labs in Florida. And I'll just show you the video snippet here, which shows how virtual agents can also affect the real world surrounding around them.
The first interaction is based on a robotic golf ball. Through a weight shift inside the outer shell, the ball can move with 3 degrees of freedom with a maximum speed of 1 meter per second. We designed a user study within a cave that simulated a mini-golf match between the participant and a blended agent. The animations of the blended agent were synchronized with the movements of the robotic ball, resulting in the illusion of the agent hitting the ball. The agent played the ball along a predefined path into the hole. Afterwards, the agent headed back to a table at the entrance of the minigolf course to record her score using a prepared scorecard. In this context, we demonstrated our second virtual physical interaction, persistent writing on a sheet of paper using a thermal table. The table is a custom-built device to activate thermochromic ink on a sheet of paper via temperature variation. Initially, the blended agent writes a projected score onto the sheet of paper. In the course of the minigolf match, the temperature is switched from high to low, and the previously transparent ink turns black. Therefore, when the user takes the scorecard outside of the mixed reality environment, the score is still visible as it is physically written. Participants of the study describe the experience as fascinating, more realistic, and memorable.
So for the remaining couple of minutes, I would like to give a short outlook how such blended reality spaces might evolve in the future. As we know, technology evolves exponentially, and this is true already since more than 100 years. And most prominently, most of you might know Moore's law, which is working on integrated circuits, but even before we had vacuum tubes, transistors, relays, electromechanical, which all followed this exponential advancements. And so the interesting thing, if we have exponential advancements, we can use this to predict a little bit how technology will evolve in the future. So here's just some landmarks from my talk. So Alan Turing and Ivan Sutherland. This was the first hype of VR technology around the 90s. This is more or less where we are today. And what we can do is we can make easily a prediction how technology will evolve in the next 15 years. So what we can do is we can just extrapolate by knowing that technology approximately doubles in performance every 18 months or so. That means every 1.5 years, we have double bandwidth, double storage, double processing power, and so on. And if we know that everything will be double in performance after 1.5 years, we know it's 4 times better after 3 years. It's going to be 8 times better after 4.5 years, and so on. And if you do the math by yourself, you will quickly realize that after 15 years, the machines that we will have will be 1,000 times better than the machines that we have today. And just think about what kind of problems you can solve just by waiting 15 years and having 1,000 times better machines. And one of the examples I would like to show you is the so-called graphics Turing test. The graphics Turing test is a variant of the traditional Turing test with the goal to render virtual objects in real time, which gets indistinguishable from the real world. And in 2006, Michael McGuigan estimated that this would require approximately 1 petaflop of sustainable rendering performance. So today, with GPUs and CPUs, we're in the range of 10 teraflops or so. That means being 100 to 1,000 times better. We will solve this problem, actually. So, and let me just say or show you an example what that means, being 1,000 times better in rendering. So when I finished high school in 1996, I played some time also playing video games. And this was actually one of the best games back at the time. Tomb Raider and Lara Croft was, that was kind of the best rendering you could get in 1996. Just 1.5 decades later, approximately 15 years later, being 1,000 times better, Lara Croft was already looking like this. And please have in mind, this is exponential advancement. So in 2016, Lara Croft was in-game rendering already looking like this. And this is also 4 years already ago. So I'm really looking forward to the next Tomb Raider game. But if you just extrapolate, it really gets clear that within the next 10 years or so, we will be able to render graphics environments which we can't distinguish from reality anymore. And also the form factors shrink, and there's literally every month coming out a new head-mounted display, and at some point eventually those head-mounted display will be shrink down to the size of a contact lens. And all big players like Facebook, Amazon, Apple, Microsoft, Samsung have filled in their patents on such smart contact lenses. And actually we observe already that we are at the edge of a paradigm shift, going from smartphones towards smart glasses. And you can observe for the first time in the last 15 years or so that the global shipment of smartphone markets has actually decreased for the first time. So we are at this edge of really a paradigm shift in the way how we as humans interact with computers and what kind of technology we use to explore the computer-generated environment. To sum up, I think that in particular, the human imperfection is the key to build mixed reality experiences in blended spaces in which we can bring together reality and virtuality, as well as human and artificial intelligence, to just provide very convincing and hopefully usable and useful applications in our field. So thank you so much for your attention. Here's a picture of our group who contributed to a large extent, of course, to everything which I showed you, and our sponsors here, which I also would like to thank you. Thank you, everybody, for your attention.
Thank you, Frank. Very inspiring keynote. So please feel free to use the chat to ask your questions. I might also remind you that you can enable your video in Zoom. So we give you those permissions, and please feel free to just raise your hand. If I see it, I will give you permission to ask your question directly. Okay. So I've seen that a couple of questions have already started coming in. Just to start us off, so I'm always amazed when I see your presentations, Frank, at how much the field of virtual reality and augmented reality has benefited from this cross-disciplinary and convergence research between fields like computer science, psychology, engineering, nowadays even AI and IoT and those fields. And your work, to me, is always a great example of a successful, let's call it, cross-pollination between those fields, right? They can help us, we can help them, and together we are bringing more to the table than either of those fields could do by themselves. So let's maybe start with our first question. See, all those questions are pretty long. If you want to ask them directly, I'll give you permissions to do that. Maybe that's faster than for me to just read your question. Maybe start with the first question. Kong Su, Kim, I think you had one. Just enable.
And also Henry is crazily waving his hands to answer a question, so he should be next then.
Okay, since I'm not hearing Kong Su, let's switch over to Henry.
Thank you. I loved your talk, Frank. I always learn stuff whenever I hear you talk. By the way, first thing I want to say is, here we're at a conference on virtual environment and is it teleexistence? And we don't use even the primitive technology we have for fear of what? For fear of being Zoom bombed? All right. Mm-hmm. We have here people from all over the world, and we could be together, and we turn off our video, which I think is so sad. Okay? How are we going to get to teleexistence if we can't even get video on? Okay? Mm-hmm. End of rant. I love your talk, Frank. I have one small suggestion, which I think is so, one of the many things that you showed that was so inspiring was the intelligent agent and how as she gets more imperfect, whether it's appearance, or in stuttering or in looking away, that she becomes more realistic and compelling to us. The one thing that still remains, as I'm sure you're well aware, is that the lips and the movement of the lips and the synchronization with this is still difficult. I'm wondering if we could take advantage of the fact that everybody needs to be wearing masks and put a mask on that agent, and then it would just move the same way because we know about cloth modeling, and it would appear more, like the times.
Yeah, that's a very interesting idea of making use of the Corona situation to also improve the overall virtual experience with interacting with agents. But yeah, you're right. In particular, I mean, the uncanny valley, and it also shows in particular that for motions, this uncanny valley is even more critical. And this applies, of course, to all the information for which we naturally learn to interpret the movement. So in particular, we have a specific area in our brain which is responsible for detecting faces. So we are really, really sensitive to some inconsistency here in the eye movements and in the lip movements. There is libraries for Unity like lip sync, which you can use, for example, to have at least a reasonable movement of the lips. But still, you're very sensitive and realize something is going on here. On the other hand, I have to admit that we as Germans are not so critical when it comes to lip reading because when we watch movies, we typically see them in a translated sense. So I have learned that the lips do not need to match the language so far. So that might be one trick. So to ensure that you do not translate or translate movies to your formal language. The other idea is also very nice by using a mask, for example, or some other means like a beard, which just prevent a little bit that we can actually see the lips, for example, but still you have the eyes. And I think in particular, the eyes of the agents nowadays are also always looking a little bit odd. But again, you can use glasses, for example, to also get a little bit away of this visual information. So I really like this idea of making these agents a little bit, it's not really making it like less realistic, but make use of certain artifacts that we even have in the real world, which can kind of occupy our view to the imperfections of our agents.
Yes, thank you. If I just may follow on what you were saying, is that I'm inspired, like you are, by various filmmakers, and they've used these kinds of techniques, of course, for many, many years when they're not able to get, for instance, the real actor has already left, and then they have, a stand-in. They don't show the stand, then they shoot it far away, they shoot it from the back, they shoot him running away. There's famous scene in Third Man in Vienna where the Orson Welles is running away. They didn't have Orson Welles anymore. So one of the assistant directors just stood in for it.
Yeah.
Thank you again for your talk. I really, really liked it.
Thanks, Henry.
Thank you. So let's try this again. Let's try it with Kangsu.
Hi, Kangsu.
Can you hear me okay now?
Yes.
So thanks a lot for a wonderful and inspiring talk again, but kind of silly question that I had. So where do you think this intelligent agent work was going? Actually, I mean, do we really want to have like a real human? Or, I mean, in some sense, it's better to keep the intelligent agents a little bit different from the real person so that we can identify the characteristics or the special features of the intelligent agent. So I wonder what you think about that. And then another question that I have is a kind of like a generation difference. It's always we always have this kind of question, but so our like next generation, the younger generation might have totally different understanding or perception of the perfection. I mean, of course, a human has imperfection about the sensory aspect, like perceptual aspect, but in terms of the social behavior or whatever the human behavior, my son might have totally different concept about the human behavior based on his experience at this point, like especially about the new normal area. So I wonder what you think about that.
I think those are both very interesting and important questions, and I would like to answer them in a shared or put them together in my answer. So first, the question, do we really want to have like intelligent agents which we can't distinguish in terms of their intelligence from human beings anymore? I don't think that this is the goal. Yeah? And it's really important to really emphasize all the time that an AI that we build always only simulates intelligent. So they will never be intelligent per se. They simulate they're intelligent. And there might be in the future simulated that well that we can't distinguish this intelligence from the intelligence of a real human being anymore. And I think for several applications, it makes totally sense to have such a behavior of an agent. If you think about a trainer, a coach, which instructs you at home, a teacher, an educator, and so on. But still, there is a very important question, which is, do we have as a community to develop those environments, as you mentioned, in such a way that I'm always aware that this is just an agent, yeah, by just displaying something on top of the agent, like this is virtual Henry, this is virtual Frank, or something like this. And I think that's a very ethical question, but the question is already there today. If you think about images, videos that you see on the internet, you also don't know if they are real or fake and have been kind of computer generated. Yeah? So we have this problem already there, but I totally agree, it really gets emergent once we have a situation in which this is all blended together in the same space and we wear contact lenses and cannot be sure if the person in front of us is a real one or not. And therefore, I think that's a really ethical society question. How do we deal with such situation? And this, of course, applies to your son, to my son, who will probably grow up in a world in which they will just experience computer-generated environments which they can't distinguish from reality anymore. And they have never actually learned in their brain to distinguish between reality and virtuality. Yeah, so for 200,000 years or so, the world in which we have been born was completely identical to the world that we left. But now it's completely the opposite. So it's changing everything so drastically, and we haven't really learned with our brain to come and work with such dramatic changes.
Thanks a lot.
Okay, so let's hear our next question from Hugo.
Yeah. Okay, thank you. Well, thank you for your presentation, Frank. I was wondering about the next challenges about gains in general, because there exist several ways to manipulate the virtual camera by applying either translation, rotation, curvature, bending, or we could even consider like time-dependent gains or gains dependent on the space configuration. And as you said, the vision is the cue that which is predominant when there are sensory conflicts. And I was wondering, do you know, or if there exist studies, or have we already considered to take into consideration other external cues or information about what we can get both in real and virtual environment to have a better understanding of gains or create new type of gains or to improve redirection techniques?
So I think regarding gains, a lot of the potential techniques have already been introduced, but there is also a lot of other interesting thoughts how you can introduce external stimuli, like using galvanic vestibular stimulation, for example, in which you apply weak signals to the vestibular sense. There has been shoes, for example, which use robotic devices and bring you kind of back. Iwata has presented a lot of those locomotion devices. And I think also, since we have now large field of use, we can also make use of redirecting our own body parts, like our feet, for example, and display them with a slight offset, combining those with robotics on the other hand. I think that might really be the key here to solve the issue of redirected walking, because I'm pretty sure only with gains alone, we will never be able to have an infinite virtual space which we just explore in our living room. Yeah, so we need some other means of technologies. And what ICAT just did last year, which was also super interesting, was using TDCS, so very weak electrical signal applied to the parietal frontal cortex, which is important for navigation. And actually it didn't work. However, we could find an effect on the gains. It didn't work in the way we thought it would work, because we think we focus too much on the spatial cognition rather than the actual visual information processing. But this is something I would really like to explore by also using small electrical signals which kind of disturb the information processing, for example, manipulate how you perceive the optic flow.
Okay,
and I have to admit, we had 2 different ethic approvals for doing that. One was just checking cyber signals and head-mounted displays, and the other one was checking applying weak electrical signals to your brain.
Okay, thank you for your answer.
Okay, thank you for a nice question, Hugo. We have time for one more quick question, and then we will move the questions and answers to Discord. But first, let's hear our last question. In Zoom, Ryan, you are.
Yeah, thanks. It was a really interesting talk, Frank. I have a quick question that's kind of a little philosophical. So this is related to this idea that you can make intelligent virtual agents less intelligent, right? To have more human-like behaviors where they're not precise, they're maybe sure of things they shouldn't be sure of, and not sure of things that maybe they should be sure of, to make people believe them and perhaps trust them more. So there's this kind of strangeness that now this is a less effective virtual agent because it's not providing you the exact information, but we believe it more, so therefore it is more effective. Do you think this is a temporary thing that we just need to, like, collectively as humanity, as users, learn to trust more perfect, exact virtual agents? Or is this something that we need to deal with and we can't overcome?
That's a very interesting question. So if we can train ourselves to trust artificial intelligence more. So I think nowadays there is a really hesitation to trust what AI and machine learning is producing. And we really don't understand in many cases how the algorithms work and how they come to a certain conclusion. So I think at least in this intermediate state in which we don't have really explainable AI or trustful AI, it might be a good compromise to also show a little bit the uncertainty of the AI system, because also the AI system uses probabilistic approaches. So they are uncertain, but very often they give us their answers in a very definite way. So I think this might be one approach to visualize the uncertainty of the agent, for example. And I think that also in the future, AI systems will always have some sort of uncertainty. So it might be nice to also display this uncertainty in a more natural way rather than using some strange visualizations which use transparency or colors to for example, show this uncertainty. But I agree, I mean, we are currently probably the first generation who will learn to interact with intelligent agents which will look like human beings, and we will see them more and more often. So it's a really philosophical, very interesting question, how we will interact with such agents in the future. So thanks for this comment.
Thank you.
Indeed, a very inspiring direction for future research. So this concludes our session, and please everyone join me in thanking our keynote speaker again.
And thank you guys for the really good question. Give me 1 minute after the presentation to come to Discourse, so I need to connect there and then we can continue discussing. Thanks guys.
Okay.